All right. Well, thank you everyone for joining our seminar today. For your information, the seminar is being recorded and will be made available on the RemPlex webpage. And as a reminder, we request that you please keep yourself muted during the presentation and the Q&A. My name's Alicia Gordon with the Pacific Northwest National Laboratory, or PNNL, and I'll be moderating today's seminar on behalf of the Center for the Remediation of Complex Sites, or RemPlex. RemPlex is a PNNL platform that couples unique core competencies and expertise with state-of-the-art facilities and physical assets to develop, mature, and deploy advanced technologies to solve complex issues of contaminated subsurface environments. And so today's seminar by Nick Atherton and James Graham from Sellafield will discuss the Magnox Swarf Storage Silos legacy waste storage facility at the Sellafield nuclear site in Northwest England. The seminar will cover the leak management plan, in situ chemical treatment, groundwater capture, ex situ treatment, results from laboratory testing, and also the potential benefits and detriments of these techniques. And first we'll have Nick Atherton, who is a chartered environmentalist, and he has spent much of his career on the protection of ground and groundwater, on site characterization and remediation. And he has worked in the nuclear industry for nearly 20 years, many of which have been at Sellafield. Also, we have James Graham, who is a geoscientist with a PhD in geochemistry, and who also has 20 years of industrial experience in land quality and geological disposal. James's career has covered land quality issues on UK nuclear licensed sites across the entire fuel cycle, including reactor research, fuel production, enrichment, reactor processing, and low-level waste disposal. And so today, after the presentation, I'll facilitate the Q&A with Nick and James. So I encourage you to please type any questions that you have into the chat box during the presentation. And so with that, I will turn it over to Nick to kick us off. Nick?
Thanks very much. So just to introduce the presentation today, really, I'll start off with a bit of an introduction to Sellafield's site, before we then focus down on the Magnox Swarf Storage Silos. So I'll give you a bit of a background to that building and the facility and what the building does, and then we'll start exploring some of the issues that we've got with the facility and particularly the potential for liquor leakage from the building. And part of what we're going to show you today is some of the work that myself and James did a few years ago, sort of 2014, 2016 sort of time frame, where we were looking at a leak to ground mitigation strategy. But as part of the presentation, I'll bring it back up to sort of current events on the facility, and we can have a little bit of a look at what it means in terms of how we're managing the facility at the moment. So for those of you that are not familiar with the sort of UK geography, the picture on the top left there shows the United Kingdom, and the little spot in the northwest corner is where Sellafield is. So it's next to an area called the English Lake District, and the diagram on the bottom right hand side shows where that is. It's a mountainous area with a number of lakes, and the site's sort of situated on the coastal plain next to that area, so that has an influence on some of the sort of local geology and hydrogeology that we experience at the site. An aerial photograph of the site itself. It's quite a compact area, over 120 nuclear facilities in a couple of square kilometers essentially. There's several reactors and a couple of fuel reprocessing plants, one of which is still in operation today, and it's the Magnox reprocessing plant and the associated facilities that the Swarf Storage Silos were originally built to fit with. If you look at this map here, it's this separation area in the middle here, which contains the oldest buildings, what we call the legacy facilities, As you can imagine, those facilities they're very congested. You can't really get very far from one building before you bump into another one, and also they're all interconnected as well. There's many facilities rely on other facilities to function, so it's decommissioning challenges is quite high up. So I work in the retrievals value stream, which is one of our sort of business areas where we're looking to manage and decommission these legacy facilities on our site. And I'll focus in on some of what that means for the sort of wider remediation of the site eventually. I think another point just to note on here, you can see that the setting of Sellafield is a coastal location in a very rural area as well. So we've got a lot of farming around us, and up above where this photograph is, that's when you start getting into the hills of the Lake District. And you can see we've got two rivers which run, one runs through the site and one adjacent to the site. And then you've got the Irish Sea just next to us. So the Swarf Storage Silos themselves were essentially a concrete, reinforced concrete facility. This is the original building that you can see the photograph of at the bottom left as it was constructed. And it's a series of 6 silos. And over the years, that building was extended. So there's up to 3 extensions. As they extended it, they improved the design from a containment point of view, with secondary containment added along the way. So it's this earliest building, the original building, that we've got most concerns with. It's a single skinned concrete structure, and the material itself was just tipped in to the top of those silos. So that bit you see on top of the building is the operations floor, and at the end you've got a hoist well which will lift the waste in. The waste itself comes from primarily comes from the decanning of Magnox fuel, which is a uranium metal fuel with Magnox cladding around the side of it. That decanner swarf, which you can see on the little photograph in the middle, in reality it looks a lot different, certainly after a period of storage, because it corrodes very quickly. So over time that material would break down. The silos are water filled, so you've got a lot of corrosion reactions going on, and essentially the waste would break down, release hydrogen and other gases, and also heat. It's an exothermic reaction. In the early days of operation of this building, they actually encouraged that reaction to happen, because they saw that it would essentially make more room in the building for more waste to go in. So they promoted the reactions, and that led to very high temperatures within the facility, and we think it's those high temperatures that have resulted in some damage to the concrete structure itself. The high temperature has almost caused the concrete to expand and crack. So very early on in its operational life, we saw the building leaked ground traced back to this north wall of the building, which you can see there. The leak itself lasted for a number of years, probably about 8 to 10 years before it self-sealed, and we didn't take any action to seal it, so we're not 100% sure of the mechanisms for that sealing. If we sort of move forward to where we're at now, one of our main site missions, if not the most important site mission, is to get the waste out of this facility. It's recognised that this facility is an intolerable risk, and what that means in reality is that there's an unacceptable risk from continuing to store the waste in the facility, and the priority is to reduce that risk by removing the waste. The top left photograph there is one of the retrievals machines that that we're installing into the operations floor. There's going to be 3 of these machines there, each weighing about 400 tons. We recognised when we were planning for the retrievals that putting that much weight on the facility and operating it over a number of years, particularly with a sort of degraded facility, would potentially cause some challenges, particularly with movement of the building, and by the building having known defects like these cracks and that we're not 100% sure how they're sealed, meant that we had to realise there was a risk there that the leak could restart either during that loading process or as we start to disturb the waste and remove it out. So the machine itself is just a mobile cave. It reaches down into the waste bed and grabs of material into a waste skip, which is then exported, and eventually it ends up in a 3-meter cube box. The example of which is on the bottom right hand side. This is a vented storage container that will then be stored for a number of years in the new store that we've built, also on the Sellafield site, before it eventually gets conditioned for disposal in the geological disposal facility. So just a couple of photographs just to sort of show what we mean by historic leakage. So this is again going back to sort of late 70s when the leak was detected, and the photograph on the left shows where they excavated down, and they actually found well, they got to the point where they thought they were getting to the leak point before they had to sort of pull back from the excavation because the dose rates were too high. But we also know there's other areas of the building where they've found seepages during construction activities, and we know that the historical leak was primarily on the north side, but the photograph on the right hand side shows actually the southern edge of the building, and you can just about make out some sort of seepages that have come out of that side as well. And as part of the construction of the first extension, they've had to build a bit of a wall just to hold back that liquor, otherwise it would have flooded their excavation. So as you can imagine, the liquor within the building, in contact with the Magnox Swarf and potentially some Magnox fuel pieces, results in quite highly radioactive liquor. From a leak to ground point of view, it's dominated by cesium, but there's lots of other radionuclides of potential concern in there, which we'll have a look at in a second. When we realised, or when we focused in on this risk as part of the retrievals activities, we realised we needed to come up with some sort of leak to ground management strategy, and that's the work that we're going to sort of concentrate on for the rest of the presentation. We started a program called the Ground Environment Management Scheme, which looked to adopt a hierarchy for managing the leak. As you can imagine, our preference would have been not to restart the leaks, so we put some efforts into improving the facility as best we could, but recognizing that it's a very old facility, and your options for preventing leakage are quite limited, while still being able to sort of retrieve the waste, which is the prime mission. So the hierarchy then focused on being able to detect a leak and minimize the consequences of the leak. And that led us to investigate some of the sort of in-ground mitigation options that we're going to explore in the presentation. So this is a bit of a schematic from around the building. It shows it extends about 5 meters below ground, and our monitoring data has allowed us to sort of piece together a bit of a picture of where the historic contamination is. Most of the cesium contamination is staying quite close to the facility and is retained above the groundwater level. Quite a high clay content in the Sellafield soils, so we're fairly confident that material is relatively immobile, and what we're really seeing in groundwater is is dominated by more mobile radionuclides. And we've got quite an extensive groundwater monitoring network, which allows us to track and trace that groundwater contamination. That's dominated by strontium close to the building, but we know there's other more mobile species in there, like technetium-99 and tritium, which we see in the groundwater monitoring results as well. So the GEMS scheme, working with some subcontractors, we went through an optioneering process really. In phase one, we had a range of options that we were looking at. We quickly down selected those options into the ones you see in phase two there. They're focusing much more on mitigating that groundwater plume that's coming away from the building. Some of the local solutions, such as barriers and cut-off walls, we realised, or we were advised at the time, that the health and safety implications of trying to install one when we've got such high dose levels next to the facility just would have been fairly intolerable. So we focused on systems that were going to offer us some sort of mitigation to that groundwater plume and prevent its spread off-site, control its spread. And that led us into three main technology areas: permeable reactive barriers, in situ chemical treatment, which is a similar version as permeable reactive barriers, but injecting the material into the ground to retard the contaminants in the groundwater, and then a more traditional groundwater pump and treat system. We recognise that surface capping may also help us with some of these schemes by preventing sort of rainwater infiltration, but it was never going to be a solution in its own right. And by focusing on the groundwater, we're really then focusing on a small number of mobile radionuclides. The list at the top here are the main ones we identified, although there is other radionuclides that are known to be in the liquor. But these are the ones that really cause the most off-site risk. So the cesium one, like I say, is staying close to the building, so we're not really targeting that for remediation. We're more focused on the tritium, carbon-14, strontium-19, technetium-99. As many of you will be aware, that various different chemical behaviours of those radionuclides, so having one scheme to treat them all is potentially quite a challenge. So that's sort of the sort of a challenge that was set really to sort of James and his team when we got them involved in the work. All my slides are stuck.
Okay, shall I take over, Nick?
Yeah, thanks, James.
Okay, thank you. So I'm going to discuss some of the experimental program that we did on the three down-selected techniques. But first of all, I'll just give a little bit more of an overview of the Sellafield subsurface. So, as Nick mentioned, there's this separation area in the centre of site where MSSS is, and beneath that, the geology is dominated by glacial deposits, superficial deposits, comprising, where sands, gravels, clays, and beneath that there's a Triassic sandstone bedrock. The hydrogeology is very, very complex at site. We think there's some anthropogenic recharge from leaking non-radioactive water supplies that causes a groundwater mound under the site, and it kind of results in potential flow in numerous kind of directions away from the separation area. There are some quite persistent clays in parts of site as part of infills from eroded infill deposits eroded out of the underlying sandstone, and they effectively act as intermittent barriers to contaminant transport to depth. We typically think like a shallow pathway, basically, that goes across the top of some of these clays off towards the sea and towards the river receptors is the primary one that we're interested in. But we've got to be cognizant of potential risk of contamination getting into the deeper aquifer also. So in terms of the actual experimental program, none of these techniques have been deployed on a nuclear site in the UK before. So we're very much in the early days, really. Sellafield has adopted the technology readiness level with classifying technology development, and we're really here in this set of experiments, taking ideas from other from other sites and other learning, and looking really to see whether at the low TRLs, the TRL3 and TRL4, whether these techniques can kind of work with Sellafield soils and groundwaters. So very quite early days in the development of the techniques. We don't obviously have, because these were done for a potential of future leak, have any actual deployment locations etc. in mind yet. So clearly it's not the stage to go into kind of detailed design or anything like that. So in terms of a bit more background about Sellafield soils and how we got some representative sediments, on this diagram we've got some borehole mineralogical data at the bottom showing these glacial deposits are quartz dominated with some some other secondary minerals, feldspars, etc. There's a reasonable clay content in some, and a mica content in a reasonable amount of airlite, which seems to kind of take out most of the cesium in the historical leaks. And but overall the cation exchange capacities aren't that high. Certainly strontium is able to move at moderate kind of migration rates really through the groundwater. On the diagrams there, it shows actually the facility. The left-hand diagram shows a little cross-section through some boreholes that were put in to trial the electrical resistivity tomography technique that we were looking at for monitoring plumes. And the blue arrow in the center figure shows just one borehole where we actually managed to get some samples out through a historical strontium plume. Well, an actual strontium plume, and from the historical leak in the 1970s. That kind of shows, there's a lot of, like I said, mixed glacial deposits, sands, gravels, clays, but it does show in some locations it really does get quite gravelly. The blue on the PSD plot on the right, the blue is showing the greater than 2 millimeter fraction, and you can see the red line there actually starts to correlate with where the coarser grain deposits are, showing preferential flow away from the building in some of the coarser grain deposits. So moving on to the groundwaters, Sellafield groundwaters are typically oxic, typically a little bit under pH 7, and they're dominated by a calcium bicarbonate signature, but with other cations and anions, sodium and chloride, etc. We made a simulant up for one of the boreholes just adjacent to that cross section I showed on the last slide. And for some of the experiments we were using such large volumes, we actually made up we took some physical groundwater samples from a non-active borehole on site. For all of them we spiked in contaminants. We actually used strontium 85 as an analog to strontium 90 just for speed of analysis, and also discriminate against the strontium 90 that was already in the soil samples. And we also spiked in Tech 99 and carbon 14. So I'll go through a bit of the pump and treat next. We're just focusing on the experimental program in this presentation rather than any of the associated kind of desk-based studies. So the pump and treat treatment stage that was adopted was a two-stage softening followed by an ion exchange removal for strontium and technetium. I'll just go through the results of both of those stages in the next couple of slides. So on the water softening, we used lime and soda ash to try and remove primarily to remove the divalent competing ions in preparation for the polishing stage. So we were trying to remove out those calcium and magnesium as calcium carbonate and magnesium hydroxide, and we did that with we tested that in a series of 1 litre batch tests using the spiked groundwater sample that I mentioned a bit earlier, and we calculated a nominal dose for those, but we also looked at a range of nominal doses around that just to see what what variability and effectiveness we got. So the results of some of these batch tests are at the bottom there, showing that we got some really good competing ion removal there for calcium. Well, certainly for calcium, the results, the tests were kind of really optimized towards the calcium removal, it being the more dominant divalent competing ion. So we were up there at the high 90% with calcium removal. And indeed, strontium being a divalent cation itself and incorporated into carbonates, it actually did a fantastic job of actually removing most of the both the natural strontium and the spiked in strontium 85 from the solutions with similar removal rates up in the high 90s of percents. As you'd expect, there was some, effectively no removal for technetium 99 in these tests. We also did track C14 in these. We didn't have any precautions though for loss of C14 to the atmosphere during them. So while we've got some removal from those, we haven't been able to quantify which of those actually went into the carbonates and which were just lost to atmosphere during the test. So onto the polishing phase, we looked at a number of media for both Tech 99 removal and strontium removal, and they're listed those there, and we kind of adopted effectively typically a matrix approach, but the results are presented on this slide really separate down to what were specifically added to treat strontium 90 or strontium 85 in the case of the experiments, and Tech 99. So these were done by some small scale batch tests, and resulted with a number of media loadings to get isotherm results, and we got very good very high KDs. Distribution coefficients were calculated for these. They differed from one media to the other. For the strontium, we got the best results with strontium treat, and while it was a bit more variable for the Tech 99, actually this RILEX gave the best overall results over the solid media loading range. But actually all of them were successful in removing the target contaminants down to the down below drinking water standards, apart from where we really didn't add a lot of media to the tests. So I'll move on to the PRB and the in situ treatment zone testing now. So we had a look at a number of both solid and liquid amendments for technetium and strontium. We were focusing on for the solid media on ultimately on looking at a soil mix type deployment. We looked at experiments in a matrix style approach. So what I mean by that is we tested all of the solids for both technetium and strontium, even though some of them were specifically to target, one radionuclide or the other. And I think that just allowed us to see whether there was any benefit for some of them, or even potentially any interaction between them ultimately, or detriment. We tended to do these set of experiments as initially as some batch tests to look at reaction rates or isotherm type tests, and then for some of them we upscaled them a bit to a column testing to kind of really look at how they performed under some flow, which were done due to project timescales, etc. At typically very upper bound site groundwater flow rates, or a bit accelerated really, and that they were run over like a month to nearly 80 days. So I won't go through all of these experiments. I'll just pick out a few to give a bit of a flavour for what we were kind of finding effectively. The liquid amendments for the column testing, I guess we'll get onto those, but we kind of plan those as a set of staged injections, building up some equilibrating the columns to start with, for instance, with the groundwater simulant, then adding in the amendment, and then often doing a kind of a flushing stage, and then a contaminant injection into the treated soil effectively. That was a kind of a typical approach. So I'll just go through some of the solid and liquid amendments that were selected. We've got a ZVI, GAC for solid amendments for Tech 99, and we also looked at sodium diphenate as a liquid amendment for technetium, which is the objectives of that type of technique are to reduce mineral phase iron from iron 3 into iron 2 and form a effectively reducing zone. And we'd seen some literature that where that had been done for some contaminants. I don't think I saw any for technetium though. But we thought we'd have a look at that. And for strontium, we selected a solid apatite, or in fact it was a bone char style apatite, and also a zeolite. And well, two types of zeolite. In fact, one of them was just off mineral suppliers, and another one was a type of zeolite that's used in our in the Sellafield site ion exchange facility, which is a very large facility on site that treats the majority of the strontium bearing site effluent. And we also looked at a technique being developed in the US for strontium, the apatite sequestration via injection of calcium citrate phosphate solutions. So I'll move on to some of the techniques and results to start with. Just some example of some reaction rate tests here for technetium that shown that we got very, very good rates and levels of removal from solution for both GAC and for ZVI, and as you'd expect at the bottom there, no removal at all for clino or for the two types of clino, basically the 6-ep clino and the supplied clino. And what was quite interesting, I guess, though, was that for the bone char apatite, we actually got some pretty good levels of removal, even though that was included as a strontium removal technique, and it probably maybe reflects a bit of organic carbonaceous material in that apatite as opposed to a mined type of apatite. But we're not fully able to explain it, but it was quite encouraging that had potentially multiple purposes there as an amendment. Okay. So then we took these on to column testing, and you can see on this plot the orange lines there on the left show the actual flow of an amended technetium through the column there, showing that they come through at a very, virtually instantaneously, just within a few pore volumes, showing that Tech 99 is is present as a oxidized in its oxidized state at in the experiments, as we expect in the Sellafield groundwater. And as opposed to that, the adding amendment shows that both GAC there and ZVI showed very good removal over the experimental timescale. And the appetite that I mentioned, we showed that in the batch tests had some impact, showed showed a reasonable amount of retardation, but obviously not anywhere like the main media that we were using to target Tech 99, which was the GAC and the ZVI. Onto the liquid amendment, the dithionite testing. This is showing some of the column results, showing again the natural soil removal on the left, and also a bromide tracer in the blue. And the lines along the bottom are showing two columns with the dithionite results in the red, and the kind of purple squares there effectively, and that's showing that the dithionite treated soil really over this number of pore volumes showed complete removal down under the detection limit, so it was highly effective over that period of time. However, we did actually inject some allow the influx of some oxygen into the experiments at about 180 pore volumes, and this plot here is just showing the impact of that on the experiment. So while we had the normalized scale up to 1 on the previous slide, showing the levels that unamended technetium got to, on here, following the oxidation, effectively the columns start to discharge the technetium out into solution quite rapidly, and to the point it actually reached 9 times the influent, the original influent technetium 99 activity. So effectively it showed very rapid and full discharge of the removed Tech 99 through reoxidation. It's clearly questionable whether that's realistic of a kind of a deployment scenario, but I think it just showed that these kind of systems are quite potentially sensitive to reoxidation, and that's kind of a risk and an issue that needs kind of looking at in the longer term if we're going to take these technologies further. So moving on to the strontium amendment, they're all displayed as strontium 85, as that's what was in the actual experiments. So these are looking at the actual solid materials that were focused both on strontium 85, and the other ones that were included just for interest to the technetium focused media. So for the strontium 85 reaction rate tests, we got very, very good removal for the 6-ep clino, and also for the apatite media, which actually on this graph underlie the 6-ep clino results. Very, very high 90% removals, and it seemed, in fact, over with very good rates of reaction there. Quite rapid absorption. Interesting for some of the other media. The clino that was supplied effectively from the internet was wasn't so good. It was still pretty good there, up into the 90%, but definitely not as good as the site clino supply. What was interesting was we did get reasonable removal with ZVI. And we also got some removal with GAC, but those results from 40 to 60% are about what you get off the site soil. So it's not really you know, adding anything to the system really. So in the strontium 85 column testing, that's shown in these graphs. We've got the very left-hand curves there showing the tracer removal, and then we've got the red and the blue points showing how strontium goes through naturally through the column experiment. So we're getting some retardation there, reaching kind of an equilibrium after somewhere over 200 pore volumes. So we've got some results there for both the apatite and the 6-ep Clino, which were both very promising during the batch tests. And the 6-ep Clino is, as per the batch test, showing very, very good rates of removal there at the bottom, and you know, over 1,000 pore volumes. It was interesting though for the apatite that the results weren't so good, and and they went on for quite a long time. These, I think, you know, these were up around the 80 kind of day in totality, and there were a couple of disruptions in the column testing over Christmas periods and things like that, where we couldn't sustain them, unfortunately. And it was interesting when they were restarted, both of those. There wasn't really a blink of a difference on the 6-ep Clino testing when we changed them. But for the apatite, it showed much greater levels of uptake following you know, of removal from solution following these periods of downtime, and that with the results in general in the comparison to the batch test showed that the apatite definitely had some kind of kinetic controls, so or you know, controlling the removal of strontium 85 from solution. So what seemed from the batch test to be a promising media actually for the, you know, under kind of quite rapid flowing conditions in the column testing, it wasn't performing so well effectively. So it was something to kind of a bit of a take-home message, I think, that came out, that certainly at the higher flow rates, Sellafield may be a more rapid reacting media like 6-ep Clino might be useful, particularly in the kind of gravelly deposits where we might expect some of these higher flow rates to persist around the MSSS silos. So now I'll move on to the calcium citrate phosphate amendment. That's to try and get some apatite formation sequestration in the ground. We kind of followed what some of the tests that we'd seen, you know, in the literature. To start with, we looked at just trying to kind of trying to get some apatite to form in some batch tests, and we did these tests here, which were simply to look at the removal of both the complex and citrate from solution there, along with some cations and anions that are incorporated into the apatite itself. So phosphate and calcium, for instance, and also just levels of strontium removal. So these were encouraging. In these tests, we got you know, quite rapid rates of citrate removal in contact with you know, this is a soil in contact with groundwater simulant and the amendment solution, and we also got calcium removal, strontium removal, and phosphate removal. So all the kind of components were kind of behaving as we'd expect. So we were quite encouraged by those results, and we moved on to doing some you know, initial column testing on these. Effectively, we looked at the kind of removal time period and used those to build up an equilibration phase effectively for the column tests for how long we'd stop the column functioning to allow the amendment to react with the soil in the columns. So that was the kind of phased approach we did in the test. We'd equilibrate them with site groundwater. We'd add the amendment, stop the column, leave it for a period, start it again, flush out the amendment, and then add strontium, the strontium tracer back in effectively to see whether it was retarded. These results, so the blue and the red are the untreated strontium soils, and the orange and the kind of pinky lines are a couple of columns that we're looking at the calcium citrate phosphate amended soil columns. And yeah, unfortunately, the results weren't that great. We did get a delay in the there was some added retardation effective to the soils, so they were looking at the normalized concentration at 0.5. The duration there went from 100 up to 200, but ultimately the results were quite disappointing and weren't really indicative of a great of a experiment that had really been successful. Clearly, we did a lot of monitoring for other parameters and things along with the strontium itself, and we actually found that the citrate removal during the column testing wasn't actually as good as we'd seen in the batch tests, and I think it effectively implies we didn't get a great precipitation of apatite in our columns as we suspected we had in the batch test. One thing we also actually noticed was we did get some reddening of the effluent that was coming out the columns, and that was suggestive of maybe some iron reduction in the columns over the period of time when we'd isolated it. And we started to think maybe that there'd been some reducing conditions develop in the column during the testing, and we wondered whether that inhibited effectively the citrate degradation and the associated apatite precipitation. So yeah, there was some lessons to learn, I think, on that. They were preliminary tests. We didn't get the opportunity to do more and to see if we could overcome these issues. So a bit of a shame about those, but we certainly learned plenty. So over to you there, Nick, I think.
Thanks, James. Yeah, so the results of those experiments plus some of the other work that we did show us there was a range of sort of reactive media out there that we could use as part of these mitigation schemes for both in situ treatment and ex situ treatment. We're I suppose particularly encouraged by the potential for carbon-14 treatment from the ex situ water softening phase as well. It was really the only technique that showed any sort of carbon-14 decontamination. So and we know from our risk modeling work that carbon-14 can dominate some of the offsite risk that we see from the discharge into the wider environment. We kind of use these findings really to start then underpinning our risk management plan. We felt confident enough from this work that we could mitigate a leak. We were slightly concerned around from a strategic point of view of immobilizing long-lived radionuclides in the ground using the in situ techniques. That sort of potentially led us to thinking that we may struggle to ultimately clean up the site at the end of the day if we were immobilizing large quantities of technetium very deep into the ground. The likelihood is we'd have to find a way of remediating that later on. So yeah, there's still some work there really to understand how, if we were going to mitigate a leak in the ground and prevent groundwater movement off-site, how that then fits in with the wider site cleanup activities that we've got planned as part of the overall decommissioning. Sort of fast forwarding a little bit then, so that, just a reminder that this work was done sort of 2016. If we look forward then to the sort of current situation now, I mean, the retrievals of the waste still our #1 priority, and that's due to start this year. But as we've prepared to start that waste retrieval, we've actually detected leakage from that original building. Similar sort of rates to the leaks that we saw in the 70s and 80s. And that's really focused everyone's mind now, as you can imagine. We've got a real life situation going on. We've enacted the other parts of our management plan, so we're focusing at the moment on monitoring and characterization of the leak. As James mentioned in some of the introductory slides that he presented, the development work really just concentrated on proof of concept, and we kind of felt that until we really understood where the main pathway of migration was, it would be very difficult to take those schemes any further and into a detailed design phase. So we felt that having some good underpinning from the site monitoring works would be needed to allow us to finally select an option and then take it through the development. And since 2019, we've not really seen any contamination in the wider environment outside the building yet. Either means we're not waited long enough yet to see that, or we've not quite got our monitoring program right, or potentially that the background levels of contamination are high enough to mask any contamination from the new leak. One thing's clear is that we did a lot of this work previously for developing the management plan on the sort of proviso that we'd get ahead of ourselves a little bit, but when we've got to the real situation and with the sort of regulatory scrutiny and site owner scrutiny that you get from that real situation, people want us to go back and relook again. So we've gone back around the loop now. We're currently reassessing the mitigation options, just to make sure there's none of the options that we ruled out earlier are going to offer us any advantages. But by doing that, we're still trying to maintain that prioritization of the risk reduction exercises, which is the waste removal. Because without that, the leak isn't necessarily going to stop again this time. It might well carry on for much longer. Okay, so I mean, just to sort of bring everything to a close, we've introduced you basically to one of our key legacy facilities where we're trying to reduce the risk to the wider public from that facility, and as part of that risk reduction activity, we've got to also manage an associated risk that the silos might leak, and so you've got an immediate risk from the hazard of the building compared to a longer term risk from groundwater migration off site. So we're maintaining our focus on the retrieval of the waste, because that's the key risk reduction exercise. But we still need to manage the risk of the leakage to ground, which is a challenge to do those two things at the same time. The work that we've presented today really sort of developed that management plan and focused in on the groundwater contamination, underpinned it with some potential technologies that we could use, and gave us some great learning from that experimental data. But like I said, the new leakage is causing us to re-look at our management plan as a whole, and as well as reinvestigating these management options. And that brings us to an end.
Great. Well, thank you, Nick, and thank you, James, for your excellent presentation. We have about 4 minutes left, and we did have one question come in through the chat from Tom Bruns from PNNL. And his question is, what is the proposed timeline for implementation of the various treatment options, including pump and treat, as well as in situ treatments?
Yeah, so we did do some work alongside the experimental work where we started to plan out what a deployment scenario would look like. We reckon we could probably get something up and running within about 4 years of starting. So that includes the sort of design of the system, characterization activities, any sort of follow-on testing and installation. But in reality, we expect once the system's up and running, we're going to need to use that system until the leak's stopped, which could be sort of many decades before the building is completely dry and empty of waste.
Great. All right. Well, with 3 minutes left, I want to thank you, Nick and James, and I'd like to thank everyone for joining our seminar today. And I just want to remind you all that the seminar will be archived on the RemPlex webpage. And we encourage you to sign up for the RemPlex newsletter by sending us an email to remplex@pnnl.gov, and also to join our LinkedIn group using the link in the chat box. And I'd like to ask you to join us for our next seminar in June on the PNNL Developed Software Visual Sample Plan, or VSP, which is a software tool that supports the development of a defensible sampling plan that's based on statistical sampling theory and the statistical analysis of sample results to support confident decision making. And so thank you again for joining, and have a wonderful day. And thank you again, Nick and James.
Thank you.
Thank you. Have a great day, everybody.